Audible?
You are audible.
So today we will start with some problems related to differential calculus and fixed point theory. So yeah, today I'll be doing some problems that are not related to the exercises in the lecture, but yeah, of course, some still they are related with the same concept. Let X be a Hilbert space with some inner product. To define function, in fact, we will call it a functional because the range is this R. We will find its derivative. Now recall, we know that the derivative, in fact, we can say that I is differentiable if we can find a linear map, differentiable at x naught, differentiable at some point x naught, if we can find a linear map di x naught such that limit h tending to 0, norm I x naught plus h minus I x naught minus d I x naught at h is norm. Now this will be norm of R because our range, our codomain is R. So here, in fact, we can replace it by just mod because in R we know that our norm is modulus. Norm h, this is norm x. This limit is 0. And then we say that this dix naught is the derivative of I at point x. So let's start with I x naught plus h minus I x naught or any x naught in x, I x naught plus h minus I x naught. This is equal to, by definition, h h. Now, by the property of inner product space, we can split the terms in between. So this will eventually be and by the symmetry, this will be eventually times x naught h plus, and this is nothing but the norm of h. So this implies I x naught plus h minus I x naught minus d I x naught h. Suppose di exists. Suppose square, I should write I is differential right in terms of equilibrium. We know that I is differentiable at some x naught in x if and only if limit if and only if there exists some di x naught from x to r such that limit h tending to 0 now I naught plus h minus I x naught equal x naught h there is equal. Is it still there?
No, it's fine now. No,
So,
it's fine.
is it, yeah, it's clear now? Just using headphones. It's okay. Yeah. Okay. Yeah, till now, we haven't done much. Okay. So, this function I will be differentiable at some x naught if and only if this limit is equal to 0. And this happens if and only if limit h tending to 0, because we have evaluated ix naught plus h minus ix naught. This is equal to 2 x naught h plus norm x square minus di x naught h by norm hx. This is equal to 0. Now from here we can see that if I define di x naught at any point h to be, in fact I'll take it to be v, to be equal to 2 times x naught v. So in that case, this and this term will get cancelled out. Eventually, we'll be left with limit h tending to 0 norm h, which will be 0 always as h tends to 0, and hence the function will be differentiable. So it is kind of back calculation. We wanted to see that whether the function is differentiable or not. We know that it is differentiable if and only if this condition holds. Now we'll look for function di such that this condition holds. So eventually we'll get the function is differentiable. So yeah, it is kind of some clever approach. Yeah. So I'll write. Therefore, if we define, we are defining dix naught on the whole space x to r as dix naught at any point y, this is equal to 2 times inner product of x naught with y. And we know that taking first term, fixing first term, the inner product is linear with respect to the second term. So eventually this will be a linear map. We'll get dix naught at h, this is equal to 2 times x naught at, and 2 times inner product of x naught with h. This implies limit h tending to 0 norm or just modulus I x naught plus h minus I x naught. And then we had minus di x naught h, this upon norm h x. This will be equal to limit h tending to 0 2 times x naught h minus, sorry, plus hx square minus 2x naught h norm h. So this will get cancelled out and we will be left with limit h tending to 0 norm hx, which will be 0. Therefore, I is differentiable at x naught, and the derivative of I at x naught at any point y is given by 2 times x naught y for every y in x. Now, since x naught belonging to x is arbitrary, we get I is differentiable everywhere, differentiable on x with, so instead of di, I'll write I dash x naught, I dash x, and at any point y, this is given to be 2 times xy for every x and y in x. So I hope this is clear how we prove that the inner product functional is always differentiable and its derivative is a linear map given in this form. So is it fine how we evaluated the derivative?
Yes, ma'am.
So this is very good, nice example. This is used generally further while solving partial differential equations. Yeah, if we'll get some time, we'll discuss some problem related to that. Question number 2. Now suppose I be a differentiable function. Suppose I defined from a space x to y be differentiable at some point x naught in x. Now let y belonging to x be arbitrary and we'll define another function phi y from r to y such that phi y t is equal to I at x naught plus ty for every t in R. So basically, you can use chain rule as well to see the derivative. I'll be using the definition. I'll be proving it using the definition of differentiability, that this function is differentiable at 0. Then phi y is differentiable at 0. So that means there exists some linear map di, and where not I, d. So basically phi y dash at 0. This will be a linear map such that limit h tending to 0 norm phi y t plus h, but this will be 0 plus h. minus 5y0 minus 5y dash 0 at some h modulus f h. This will be 0. So yeah, let's see how we'll show that. We'll use the differentiability of the functional I. Since I is differentiable at every point x naught and x, sorry, at x naught and x, this implies there exists a linear map Di x naught, which belongs to the space of continuous linear functionals bxy, such that limit h tending to 0 norm I x naught plus h minus I x naught minus di x naught at h. This is norm in y upon norm in h. This is norm in x. This is equal to 0. So let me mark this as number 1. Now phi y 0 plus h minus phi y 0. This is equal to I. So this is phi y at h minus phi y at 0. X naught plus hy. X naught plus hy. Y is minus I at x naught. Now again, we'll start with assuming that the function phi y is differentiable. Then see that what condition we need. Sorry, what will be domain and codomain here? In this problem, are you asking about x and y?
For domain for phi dash y of 0, the derivative.
Okay. So for derivative, it will be again from r to y. So basically, whenever we have a function, its derivative function is from x to y. Its derivative is a bounded linear map from x to y. It might, yeah, it should be on the domain and codomain are always same.
Okay, ma'am.
That's why, yeah, that's why here I took modulus. No? So again here we'll start with assuming that suppose it is differentiable, then we'll see what conditions we need to to get that differentiability. Okay, so suppose phi y is differentiable. Differentiable at 0. This implies there exists a linear map d phi y 0, which belongs to the space of bounded linear functions defined from R to X, such that limit h tending to 0 norm phi y 0 plus h minus phi y 0 minus d phi y 0 at h. This is norm in y. So this is from R to y, na? R to y upon modulus of h. This is 0. That is, and this happens if and only if limit h tending to 0. So this phi y 0 plus h minus phi y 0 is nothing but I x naught plus hy minus I x naught. Then we have minus d phi by at 0 at h on modulus of h. This is equal to 0. Now I want this to convert this equation in form of the derivative of functional I. So from here I can take z equals to hy. This implies since y is fixed, z will tend to 0 as h tends to 0. This is happening in x. So this will happen if and only if. Okay. Also, if I take d phi by 0 at t, this is equal to d I x naught dy. So how did we get that? Okay. We'll write this later. Okay. So this happens if and only if limit z tending to 0 I x naught plus z minus I x naught minus d phi by 0 at h, and h is some z by, instead of by we should write z by inverse upon h. This is equal to 0. Now if I'm taking d phi by 0, this is a linear map. I'm defining it for any t. This is equal to t times derivative of I at x naught at point y. So from here we'll get d phi by 0 at z y inverse is nothing but this is t times di x naught at z. And since di is a linear map, this will be di x naught at tz. So you'll see by taking this derivative in this form, we'll eventually get what is required. So yeah, this will happen. This happen if and only if limit z tending to 0. We have I x naught plus z minus I x naught minus this is di z naught dz, and yeah, here also this is, this was modulus h, no? So z y inverse is upon norm z in x times norm y in x. This is equal to 0. Now since I is differentiable, this term, this part will be 0. So I should get z here.
T should be replaced by ZY inverse there. No?
T, T should be replaced by z y inverse. Yes, so we should have y inverse also here, na? This is y inverse. And this will be dz y inverse, something like this.
In
And
place of t, no?
okay, I'm so sorry. So this is, yeah, at we are finding the value of the function at point z y inverse, and this will be dix naught y. So eventually all this is constant, and now we can take z y inverse inside because dix naught is just linear, and this will be eventually z, because y inverse y is identity. Yeah, yeah. Now this is fine. So this is z. Okay, thank you so much. Yeah, now since the function I is differentiable, this term will be 0. And yeah, again, since this is constant, so eventually everything will be 0. That's what we want. Therefore, yeah. Now, since I is differentiable at x naught, this implies, yeah, because this is independent of z, we have limit z tending to 0, norm I x naught plus z minus I x naught minus di x naught z upon norm z times norm y. This is 0. And we know that this happens if and only if the function phi y is differentiable at 0. This implies phi y is differentiable at 0 with the derivative. Instead of d phi y, I'll write d phi y dash 0. This is a linear map and it is defined to be equal to t times, yeah, this is t times derivative of I at x, ix naught at the point y. Yeah, this is how we'll get a derivative. So this function phi y will be differentiable, and its derivative, we can evaluate its derivative using the function I. So basically, if you directly apply the chain rule, you will eventually get the same. I just wanted you to see the in between calculations, how these limit and everything is done. So if you still have any doubt in any step, please let me know.
So, ma'am, this proof depends on bit much on guess.
Yeah, and that guess is not just uh, what do we say? The guess is eventually coming from what we want,
Hmm.
because we wanted this d phi y term, uh, this d phi y and all this term should be converted into this form so that we can use the differentiability of the function I. That's what we wanted. That's why we took d phi y in such a way. Yeah, somewhere you will have to think that what should we take. But yeah, in this way, this is basically back calculations. Using this back calculation process, you can guess what the derivative should be.
Yes, ma'am. And uh, whatever we will assume, we should also take it that it is a linear map, isn't it?
Exactly, bounded linear map.
A bounded linear map.
Uh,
Why, ma'am, bounded?
The bounded linear means continuous and linear map. The derivative, that's how we define derivative. Na? Our derivative is a continuous linear map.
Oh, yes.
So we call it bounded linear.
Okay. Yes, thank you.
Okay. Let's see some other problem. This is question number 3. let I from x to y be a function such that for each x in A, sorry, for each x in X, there exists a function u, which is a bounded linear function from x to y, such that limit t tending to 0, I x plus ty minus ix upon t minus ux. So this is ux. Ux is a map from x to y. So ux at y, this is equal to 0. Then, so you might feel that this is kind of the definition for differentiability. It is somewhere not exactly the same, but yes, something is related to that. Then the map x mapped to ux is continuous. So it's continuous. And no, then if the map, let me write it chi from x to bxy defined as chi at any point x is ux is continuous. If this is continuous, then our function I is a C1 function. I is C1. I belongs to C1 x y. So can you tell me what do we mean by C1 function?
All first partial derivative exist and are continuous.
Yeah. And in fact, we'll see that basically it is differentiable and its derivative will be continuous. So derivative, talking about derivative, um, so I dash, when we have I from x to y, at every point I dash x, this is again a linear map from x to y. So can you tell me if I want to define the uh, domain of I dash, what will be the domain of I dash? So yeah, domain will be x because eventually we are finding derivative at ix. What will be the codomain?
For domain, I think bxy.
Yes. So because every function, every point x, when we find its derivative, I dash x is a bounded linear function. So it will be from x to bxy.
In case of Rn to Rm, where derivative is bounded linear map from Rn to Rm,
Again,
and
same
here
I dash x naught is from Rn to Rm, and I dash will be from Rn to the space of bounded linear functions from Rn to Rm, something like this.
oh, and this is exactly the same of L Rn to Rm, no?
L,
Not
uh,
notation.
okay, yeah, they're using some other notation. No? L, were we using L of xy to the for the space of bounded linear functions, continuous linear functions?
Yes, yes.
Okay, okay, okay. So generally we use this B or BL because continuous linear functions are also called bounded linear functions. So yeah,
Okay.
in many other books you will see some notations like this, bxy. And generally lxy is used for the space of just linear functions, linear transformation.
Yes.
So we claim that I dash x, this is given by the function ux. If the claim is proved, then we'll get that I dash is continuous. How? Okay, first let's start with this part.
We fit it in the definition of derivative. I think it will satisfy.
To get continuity. Wait, let's see. So we have limit t tending to 0. So taking t LCM, so this is t x plus ty minus ix minus t ux at point y on t. This is given to be 0, and this happens for every y in x. This is happening, yeah, this is happening for every y in x. Mhm. Now, since ux is a bounded linear function, so it is linear. So this implies limit t tending to 0 ix plus ty minus ix minus ux at ty. I can take this t inside point t. This is equal to 0. And in fact, yeah, this will be mod t. No?
So from here we can say that its derivative at uh, x is ux. Ma'am, you are not visible.
Oh, I got disconnected. Yeah, is it visible now?
Yes, ma'am. Yes, now it's visible.
So yeah, let's take h to be ty. So this time, this t is actually a real number. Yeah, this t is an element in the field t times y. Na? So this will be mod t, and so this will be mod t. So this implies limit t tending to 0 I x plus ty. So ty is h now, h, and this will go to 0 as t tends to 0 because y is fixed. Y is independent of t basically. Minus ix minus ux at h upon this will be norm h times norm y. Yeah. Now since y is non-zero, so this will give us limit t tending to 0 ix
Extending to
basically.
0.
Oh, sorry, tending to 0 minus ix minus xh on norm h. Now this is 0 because everything was happening for every y. So yeah, we need not fix y to be 0. So eventually this term should be 0. And now this gives us that I is differentiable. And the derivative is given by ux. Therefore, I is differentiable at x and I dash x. This is equal to ux. Now if I define sorry, uh, therefore the I is differentiable, its derivative is ux, and we wanted to show that it is in C1. So any idea, any guesses how it will become C1? For C1, we need I dash to be continuous. So basically x mapped to ux should be continuous. Yeah, because we were given already, na? Ux is in bxy. But ux is in bxy.
X.
Basically, ux is from x to y. So yeah, eventually this will be become a C1 function. I
What is
is
given about UX?
ux is a function in bxy. So basically, ux is from x to y. It is bounded linear function, continuous and linear.
Oh,
But we
bounded
want
linear.
this map to be continuous. Basically, eventually you'll get that. I'll need to see how. I think I'm missing something. I'll have to check this. So from here, it comes directly. There is some point I am missing that if
Can we check the limit h tends to 0, I dash x plus h minus I
Something like that.
x is 0.
I dash x plus h. If we prove that this is equal to I dash
I dash
x.
x.
Yeah.
I dash x plus h is u x plus h, and u is linear, so ux plus uh.
Limit h tending to 0. This will be ux plus h. This should be equal to ux. We don't know whether x mapped to ux is continuous or not. Maybe it was a condition given in the question. I've written the question incomplete. I'll check that. Yeah, it was given now. Oh, see, this map is given to be continuous. X mapped to ux is continuous, na? Yeah, now I
Oh,
got it. Hmm. Therefore, I dash is continuous. Hmm. Since chi is continuous, we get x mapped to I dash x is continuous. That is, I belongs to C1 class. Yeah, that was the main point. No? If we have a function u satisfying this such that x x mapped to ux is continuous, then our functional becomes differentiable as well as its derivative is continuous. Are you all familiar with the LP spaces? I guess so. If we use do some problem related to LP spaces. I think we did some problems na, related to LP spaces.
mm.
Okay, we'll do one problem.
It is collection of sequences such that
No, no, no,
summation
no,
of
no, 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 not that. Capital LP space. So this is collection of all those functions such that the integral. So if I take this LP omega, such that this integral to the power p, this is finite.
oh,
So it comes in measure theory. I think this problem will be helpful for you further to reconnect the things. Let's do some. Let omega subset of Rn be a bounded open set and p is greater than 1. Now let g from R to R be a C1 function. That means g is differentiable and its derivative is continuous such that it satisfies some growth condition. Firstly, mod gt, this is less than equal to a plus b times mod t to the power p, and we have g dash t, this is less than equal to a plus b times mod t to the power p minus 1, where a and b are some constant. For some constants, a and b. Now we define I from the space LP omega. So basically this LP omega is a Hilbert space for p equals to 2. Otherwise, it is a Banach space. P not equal to 2. Otherwise, it is always a Banach space. To R, by IU. For if U is a function in LP omega, we define IU to be integration over omega G of UX. Now see, since U is in LP omega, that means U is a function from omega to R. That means UX is an element in R for every X in R. This implies, now again G is from R to R, so GUX, this is just composition. So this is GOU at X. So that's how this is defined. We'll see that this function is differentiable. Then this I is differentiable as well as its derivative is continuous from LP omega to R. And for any U in LP omega, we have I dash U at point phi, because I dash U is again a bounded linear map. This is given by integral over omega G dash U times phi for every phi in LP omega. See here, I is a map from LP omega to R. I dash U is again a map from LP omega to R. And for any phi in LP omega, this is how we define I dash U. So yeah, this is how what we'll get eventually. So this is a big
Codomain of I dash U will be R or
R.
B LP omega R.
It will be R.
Oh,
I dash U, no? Because I dash U at any point phi, this is giving us this integral. This integral will eventually be solved and this will be a real number.
okay, okay. Thank you.
So let's see how to do this. So we'll solve this problem in steps. So let U be some function in LP omega. Firstly, we define a map U. This is from LP omega to R by KU at any point phi. This is given by integral over omega G dash U phi. We'll see how the derivative of G will help us to get the derivative of function I. So basically, because here also we need to get G dash U. This is for every phi in LP. So firstly, we'll see that this I is well defined. That means this integral is finite. Step 1, I is well defined on LP omega. So let's start with modulus IU. So basically we want to see that whether this integral is finite or not. IU, this integral. This is equal to integral over omega G ux dx. Now we know that we can take this modulus inside Gux dx. And we are given the growth condition on G. See this growth condition. So this will give us, this is less than equal to A plus B. Since we had GU, so this will be less than equal to A plus B mod U to the power P. This is less than equal to integration omega A plus B mod u to the power, so I'll write ux to the power p. Now this is equal to omega constant plus b times integral over omega ux k power p. Now since u is a function in LP, we started with u in LP. So this integral is finite, and this will be finite only when omega is bounded, because that will give us finite measure. So this is equal to a times mu. Mu means measure of omega plus b times integral omega mod u to the power p, which is finite because omega is bounded. For bounded functions, bounded sets, we know that the measure is finite, and u belongs to the space LP omega. Therefore, this integral is finite. Therefore, I is well defined. Next, we will see that this function k is a bounded linear functional. This is a bounded linear functional because eventually this will be our derivative, no? Write a claim that this k that we had assumed is, so k was defined from LP omega. K was defined from LP omega to R. To R, this is a bounded, or in fact, I'll write continuous linear function. Continuous linear function. Clearly, you can see the linearity because we have ku. So this was ku at phi alpha phi 1 plus phi 2. This will be integral over omega g dash u times alpha phi 1 by phi 2. So basically by linearity of the integral, I can write this to be alpha omega phi dash u phi 1 plus integral omega g dash u phi 2. This is alpha ku phi 1 plus ku phi 2. And then for continuity, we'll be using the Hilder's inequality. Also, we have mod ku at any point phi. This is equal to mod g dash u times integral times phi, which is less than equal to integral omega g dash u phi. And by Hilder's inequality, we know that this is less than equal to. I hope you know, you are familiar with Hilder's inequality.
No, ma'am.
I'll tell you.
Holders inequality.
Yeah. So we have two dots over O, so it is called Hilder. Yeah, we write it holder, but we have these two dots over O, so its pronunciation is Hilder.
Oh,
That's U to the power P. So take this Q, 1 by Q, and then we have pi Q to the power 1 by P, where P and Q are such that 1 by P plus 1 by Q equals to 1. Now since P we had already taken, so P is fixed, so I'll take this Q. This is equal to P upon P minus 1. So taking q in this way, we'll get 1 by p plus 1 by q equals to 1. I'll just write the Hilder's inequality. We have, well, fg over omega, this is less than equal to f by lp norm. So right, f to the power p whole to the power p by p, where p and q greater than 1 are such that 1 by p plus 1 by q equals to 1, provided the integrals are finite. Provided this integral omega f to the power p and integral omega g to the power q is well defined. So yeah, so we say that if f is in LP and g is in LQ, then f times g, eventually this is an element in L1, because yeah, f times g, this is power 1 kind of thing. So this is how we have Hilder's inequality. Yeah. And from here we'll get this is equal to, now we know that f phi is in LP, so this is LP norm of phi times, so this can be treated as some constant, so I'll write this to be alpha, where alpha is the LP norm of LQ norm of G dash. Yeah, because G is a continuous function and we are integrate. G is a C1 function, so its derivative is also continuous. Therefore, G dash is continuous and omega is a bounded domain. So this integral is well defined. We take this to be alpha. So therefore, we get mod Ku at any point phi. This is less than equal to alpha times norm phi. We know that if a linear function satisfies this condition, then it becomes continuous. Therefore, Ku is a continuous linear function. Next, we will next
Norm on
step.
LP space, how it is different?
Okay, so on LP spaces, uh, yeah, and we have norm LP omega. This is equal to integral omega f to the power p whole to the power 1 by p. So this is how we define norm on LP space. Okay, so that's why this term becomes LP norm of phi, and this becomes LQ norm of G dash.
And LQ norm of G dash becomes scalar.
Yeah, it will be a constant because we know that say G is a C1 function. This implies G dash is continuous and omega is some bounded domain. So we know that every continuous function on bounded domain uh, is integrable,
Integrable.
and eventually its power q will also be continuous. So omega,
Hmm.
no, because we have, no, I don't see. There's an issue. The domain is omega, but we are applying g dash over ux. So from there we can't say. So wait, I'll write in detail. Basically, that comes due to the growth of function g.
And what is growth?
I'll tell you. I'll tell you. So now, till here it is fine, no?
Yes, ma'am.
We have integral over omega mod g dash u to the power q. Growth is the condition, these growth conditions we were given already, na? So we know that g dash t is always less than equal to a plus b mod t to the power p minus 1. So g dash u modulus g dash u will be less than equal to a plus b times mod u to the power p minus 1. So this is less than equal to integral over omega a plus b mod u to the power p minus 1 whole to the power q. Now this can be written as some const less than equal to some constant times a to the power q plus b to the power q mod e to the power q times p minus 1. This constant is, I think, 2 to the power q minus 1, something like that. Because we have a plus b to the power anything x, this will be less than equal to 2 to the power x minus 1, a to the power x plus b to the power x. Yeah, we have something like this. I think it should be x minus 1. You should check. Eventually, that will be some constant. So we can get these powers inside.
Okay.
So this will be, yeah, this is again in some constant integral over omega. So 1 integration of 1 that will give us the measure of the space omega set omega plus again some constant times mod u to the power q times p minus 1. Now q we have taken to be p by p minus 1. So q times p minus 1 will be eventually equal to p. So this is just p. Again, this is, I'll write some constant c1, measure of omega, plus some constant c2 times integral over omega u to the power p. Now since u is in LP, this is eventually finite. Again, since omega is bounded and u belongs to LP omega. So this implies integral over omega mod g dash u to the power q whole to the power q is 1 by q is also finite. So I can take this to be equal to some alpha. Yeah, this came due to the growth condition given on the function g. So this implies mod ku at 0.5, this is less than equal to alpha times the LP norm of phi. This tells us that this ku is a
Bounded linear.
continuous, yeah, bounded linear function. It's linear map. So next step 2. So till now we have just seen that what they wanted us to prove, what they wanted us to prove that this will be the derivative. So till now we have seen that this can be derivative because this is a bounded linear map. Next we will see that this is eventually the derivative of the given function. So
And u omega is measure
mu
of u
mu
omega. What you
mu
say?
mu omega mu. This is.
Mu omega.
Have you done any course on measure theory?
Actually, this course is currently going on. We
Okay. Okay. So you're not familiar with measure, then integral
yes, but
and
we didn't go there in LP space until now.
okay, okay, okay. So yeah, maybe right now you might think that these things are a bit complicated, but eventually when you'll do that, you'll realize that this was useful. So there is connectivity. So I
Okay.
just wanted you to see the derivative maps. Yeah, till now we haven't used any such. I'll keep telling you because yeah, the definition of LP space is the way we have defined norm. Measure is something. For example, we were integrating from A to B the way we do in R. So this A to B, this interval A to B, its measure is B minus A when we have interval. And when we are doing
Yes.
working in Rn, so suppose R2, we have a circle. So our measure is the area inside the circle, measure of the space omega. So you remember if we integrate 1 over from A to B, this is just B minus A. This gives us the measure. So that's how we define integral in higher order spaces. So on bounded space, if we are integrating over continuous constant function, so it will eventually give us the measure.
Okay. Okay. Thank you, ma'am.
So let T belongs to R and phi is a function in LP omega. So this is what we are claiming. Then limit p tending to 0 mod iu plus t phi minus iu upon t minus ku phi. So we need to see that this is equal to 0. This is equal to, by definition, this is equal to limit t tending to 0 mod 1 by t integral over omega g u plus t phi minus gu minus integral over omega. So ku phi is g dash u times phi. So we want this to be equal to 0. Okay, so I'll mark this as star, this whole equation. Let x belongs to omega. Consider the function h from R to R. Hz, this is defined to be g u x plus t z phi x. Now, since g is a C1 function, this will eventually be a C1 function. H is a C1 function because g is in C1. Now, by chain rule, this is just of everything real. By chain rule, we have h dash at point z. This is equal to g dash at ux plus tz at phi x times t t phi x. Okay. And h1 minus h0, this is equal to g ux plus t times phi x minus gux, which is equal to integral 0 to 1 h dash z dz. So can you see how I got this integral term? Because we know that by fundamental theorem of calculus 0 to 1 h dash z, this is nothing but h1 minus h0.
Oh, yes.
So I should have written it before. So this is, we can write it 0 to 1 h dash z dz. This is equal to h1 minus h0, which is equal to, by definition, gu plus t phi x minus gu. Okay. So from here we get gux plus t phi x minus gux. This is equal to 0 to 1 h dash z dz. And we know that h dash z is 0 to 1 g dash ux plus t z phi x times t phi x from here. So why we are doing this? Because we want to evaluate this term. So we have gu plus t5 minus gu. This is given by this integral. And that was I plus t5. So yeah, I hope it is fine till here. Now this implies I u plus t5 minus iu. This is equal to integral over omega gu plus t5 minus gu. So yeah, that's the definition of function I. And we know that this is equal to, by above, 0 to 1 g dash u plus t z phi times t phi x dz. So now since this t is constant here because we are integrating with respect to z, I can take this t on the left hand side. I'll get I u plus t phi minus iu from t. This is equal to integral 0 to 1 g dash u plus tz phi. So this phi is a function of x, t and z are independent of it, times phi x dz. And this implies mod I u plus t phi minus iu by t minus ku phi. This is
Is it
equal to
simple multiplication or dot product? G dash ux plus tj.
simple multiplication because g is a function from r to r, na?
Oh,
Yeah, g is from r to r, so it's simple derivative. So
mm.
this is equal to modulus 0 to 1 g dash ux plus dz phi x dz minus ku phi. Ku phi was integral omega g dash u x times phi x dx. So this is less than equal to integral 0 to 1. So you can see that here we have integral 0 to 1 and here we have integral over omega. So firstly, I'll convert this for integral over omega. So I'll write this modulus 0 to 1. And the inside term, I can write it as integral over omega g prime ux plus t phi x t z phi x mm, dx dz minus integration 0 to 1 integral omega g1 ux phi x dx. So this we are able to do because x and z are independent and integral over omega g dash u times phi. This is some constant. So eventually we are integrating 0 to 1 constant this term. So that will again give us the same constant. And inside we already had omega. Oh, something. Yeah, because here I had omega as well. So this was double integral. So yeah, if because this is a constant, eventually this will be a constant, and we know that if we integrate some constant from 0 to 1, we'll get again the same. Just to make everything similar, both the terms with double integral, I did that. Now this is less than equal to 0 to 1 integral over omega. So uh, this is times phi x dx dz. So I can take mod phi x common in both the terms. Then inside we have g dash at ux plus zt phi x minus g dash at ux. Here we have dx, then outside we have dz. Now since we are given that g dash is continuous, because g was a C1 function, since g dash is continuous, this implies as t goes to 0, g dash u plus tz phi will go to g dash u. So eventually this will go to 0. This implies as t goes to 0, mod phi x times g dash u plus tz phi minus g dash u, this goes to 0. Oh, so you people will not be aware of the dominated convergence theorem because we haven't done the other spaces. I think we should not do this now.
Dominated conversion.
Have
When we complete this, we will see it.
because you must have done this, read this fact that when fn is a sequence of continuous functions converging uniformly to a function f, in that case, we know that integral over f n will also converge to integral over f. But in the case of pointwise convergence, we do not have such convergence. That means if this convergence is uniformly, then only limit and integral can be interchanged. But for pointwise convergence, we can't do that. Further in we have another convergence result. I'll write that we are using. So all I need you to understand is the fact that if Fn, the sequence of functions, is converging to f in some space x, this need not imply that integral over x fn, this will also converge to integral over f x. This happens in some specific cases. For example, if we have uniform convergence, if we had uniform convergence, then we can guarantee that this convergence will imply the integral convergence. Otherwise, we have some other results how to get this convergence. So one of those results is the dominated convergence theorem. We have dominated convergence theorem. It says that suppose Fn is a sequence of integrable functions, integrable functions such that the first condition Fnx converges to fx. That means we have pointwise convergence, and along with that we have um, some dominating function. That means there exists some function g such that our mod fnx, this is less than equal to gx for every n in n and x in x. Then this function g should also be integrable. That means it is in L1. Then we have, yeah, then limit n tending to infinity integral. Suppose this is everything on x, fn x dx. This is equal to integral over x fx dx. So basically, pointwise convergence need not imply the convergence of the integrals. We have some results which helps us to get this limit of the integrals. So one of this dominated convergence theorem is very useful. So yeah, you should be aware of this. Whenever you'll learn the LP spaces, the measure, in fact, that starts with the measure theory. So you'll get to know more about this. So yeah, this is the main result that we will be using. So basically, we need the pointwise convergence and we need some dominated function. Okay.
So this is apart from uniform convergence, use of uniform
Yes,
convergence.
yes, yes, yes. If we had if this we knew that this convergence is pointwise convergence, then we need not find some dominated function. Then we can directly say that limit, and basically we are interchanging the limit and the integral. So
Yes, yes.
these are called these are the conditions where we can interchange limit and integral. So yeah, this is what we are doing. We are interchanging the limit and the integral. We can interchange when we have uniform convergence and also while if we have some dominating function. This is pointwise.
In case of uniform convergence, derivative also preserve. Example.
Yeah, derivative, I think that's direct. But for the problem is for integrability.
Okay.
Okay. So yeah, here also we'll be using something like that because we are eventually taking t tending to 0 inside. So this is the pointwise convergence. We have as t goes to 0, this is converging to 0 pointwise. Next, we need to find some dominating function. So, and we have mod phi x g dash u plus z t phi. So I should write x also. Ux plus dz phi x minus g dash ux. This is less than equal to. Now we are using the growth condition on g dash. So this is phi x and this will be so by triangles inequality, right, step by step plus dz phi plus g dash u. Now we'll use the growth condition on the function g dash. This will be a plus b mod u plus dz phi to the power p minus 1 plus a plus b mod ux to the power p minus 1. So this will be some constant times mod phi x plus some other constant times mod u plus t z phi to the power p minus 1 plus c3 times. So this will be multiplied by phi x as well. Phi plus c3 times mod u to the power p minus 1 mod. So I want you to check yourself. This will belong to L1 omega. That is, see that the integral. So this is clearly finite because this, this, here you can use the Hilder's inequality. Again, here also you can use Hilder's inequality to see that all these integrals are finite. And by using Hilder's inequality, okay, and the fact that phi and u both are in LP space. So I would that would be a an interesting exercise that would eventually help you to understand more about LP spaces and this Hilder's inequality. So this will be in L1 omega, and this should be independent of T.
Which one is independent of T?
The upper bound should be independent, this complete upper bound. But still we have T.
Oh,
We'll have to see. That upper bound will also come due to this continuity of G dash. So yeah, you can see this also. This upper bound should be independent of T, and that will come by continuity of G. You try yourself, you'll get that. So eventually, by dominated convergence theorem, this term will converge to 0 as T tends to 0. And this was, now this tending to 0 will imply that this will also tend to 0 because this by sandwich theorem, by because this modulus will be less than equal to in between the positive and negative of this term, and since this is converging to 0, therefore we'll get, therefore by dominated convergence theorem, we'll get limit t tending to 0 mod iu plus t phi minus iu by t minus ku at phi this will converge to 0. So yeah, from here we get that I is differentiable and its derivative is given by the bounded linear functional that we have seen above. So main idea was to use the dominated convergence theorem. Then we need to show that this will be continuous as well. There again will, okay, let me leave that part, we'll do later. Otherwise, I won't be able to do other problems. Let's do some problems related to the fixed point theory. We have, this is the exercise problem. Let B subset of Rn be the ball ball of radius r around centered at 0. So it should be the closed ball of radius r around 0. Let f be a function. Let f from B to Rn be a function such that number 1 fx minus fy, this is less than equal to b times norm x minus y, where this b is strictly less than 1 and greater than 0. Second condition, we have f0, this is less than equal to r times 1 minus b. Then we need to see that f has unit fixed point in b. So I think similar thing we have already done if our domain and range are complete spaces. Now this time our domain is just a closed ball. So let's see how we'll get unique fixed point in this case. Show that f has a unique fixed point in B. So yeah, we'll start with the similar proof. Let's start with f square x minus 0. 0. Now this is equal to f of 0. I'll add and subtract f at 0. So this will be less than equal to f at f of 0 minus f at 0 plus f at 0. So by first, this is less than equal to b times f0 minus 0. And this is also f0 minus 0. So this is b plus 1 times norm f0. Similarly, you see, following similar pattern, you'll get f cube 0. This will be less than equal to 1 plus b squared times norm of f0. And so on. Fn 0, this will be less than equal to So
1
1
plus
so on up to b to the power n
n
minus
minus
1
1.
f0. And this is obviously less than equal to summation n from 0 to infinity b to the power n times f0. And since b is strictly less than 1, so this is a GP, geometric progression with radius strictly less than 1. We know that this is finite and this sum will be 1
1 by
upon
1 minus b.
1 minus b. 1 by 1 minus b times fc. Now if I define a sequence yn to be fn0, then we get norm yn, this is less than equal to norm y naught, sorry, y1, norm y1 upon 1 minus b. And this is happening for every n in n. Therefore, our sequence yn is bounded. Bounded in, so yn is a sequence in Rn. And in fact, we will see that this is a Cauchy sequence. For that, yn plus m minus yn, this is equal to fn plus m at 0 minus fn at 0. So this is equal to f of n plus m minus 1, 0 minus f of fn minus 1, 0. This is less than equal to b times f of n plus m minus 1, 0 minus f of n minus 1, 0. And moving on in this same pattern, eventually you'll get this is less than equal to b to the power n minus 1 f m plus 1, 0. See here, the power of b plus the power of the first term. This is basically, this should be equal to n plus m every time. And power of b plus power of the lower term, this sum should be n all the time. So, yeah, so this is f. I hope you understood how we got this b to the power n minus 1.
Yes. It's similar to the proof of Banach theorem.
Exactly. It is the first, this initial steps is same. All you need to do is you need to find the fixed point. That point should also be a point in the ball. So now we'll eventually prove that this sequence yn converges to y naught. And earlier we used to get that this y naught will be the fixed point. So all we need to show here is that y naught should be in the ball. That is the main difference. Otherwise, everything is same. So yeah, this is less than equal to b to the power n f m 0 minus, oh, not x. This is 0. So this is therefore, and this is r b n norm of ym. Now, since ym is bounded, so I can write bounded. This implies there exists some m positive such that norm by n, this is less than equal to m for every n in n. So this is less than equal to m times b to the power n. Yeah, so taking n tending to infinity by m plus n minus by n. This is less than equal to m b to the power n, which goes to 0 as n tends to 0 because our b is between 0 and 1. We know that for some constant strictly between 0 and 1, its power n goes to 0 as n tends to infinity. So this implies norm yk minus yn, this goes to 0 as k and n goes to infinity. Because eventually m plus n will be larger than n, and as n goes to 0 infinity, we know that this goes to 0. So this implies our sequence yk is a Cauchy sequence, Cauchy sequence in Rn. Since Rn is a complete space, this implies yk converges to some y naught, converges to some y naught in Rn. Now, we don't know whether this y naught is in the ball or not. For that, also, since norm by n, this is less than equal to norm y1 upon 1 minus b, this is less than equal to norm y1 upon 1 minus b, which is norm f at 0 upon 1 minus b. And we were given the condition that norm of f0, this is less than equal to r times 1 minus b. So this is less than equal to r times 1 minus b upon 1 minus b. This gets cancelled out. This is equal to r. Therefore, this yn belongs to b for every n in n. Now, since yn is a sequence in B, where B is the closed ball, so the limit will also be inside B because yeah, closed and bounded set in R and are compact. This implies y naught is in B since yn converges to y naught, and uh, since yn is a convergent sequence, yn is a convergent sequence in B, and B is a compact subset of Rn. So its limit will also be inside B. Now we claim that this y naught is the fixed point. That means f at y naught is equal to y. So yeah, this part is again same. We have f y naught minus y naught. This is equal to, less than equal to fy naught. I'm just adding and subtracting f this n. Okay. N
It's natural language.
hmm? No, not that one. Uh, we'll use, yeah. From here, since yk converges to y naught, this implies for epsilon positive, there exists some capital N in N such that norm yn minus y naught, this is strictly less than epsilon by 2 for every n greater than equal to n. So basically, we'll be using this again. So, yeah. Now f y naught minus y naught. This is less than equal to f y naught minus f n plus 1. This n is the same as we got in the definition of convergence. This one y naught minus y naught. Now this is equal to f of n y naught minus f of y naught plus f n plus 1. So f n plus 1 y naught y naught minus y naught. So this is less than equal to b times f n y naught minus f y naught plus f n plus 1 y naught minus y naught. This comes again by first condition on the function. Now this, instead of y naught, for that we need to be 0. So y naught is yn. This is f n at 0. So I wanted to bring yn.
Hmm.
Then only we can use the convergence of yn.
Sufficiently large n.
Hmm. Yeah, basically
Does
that's the main idea, that for n tending to infinity, this
mm,
yn is tending to y naught.
ah, yn actually converges to y naught, no?
Yn, basically I think here I should write 0. Then it will be, this is 0. This is 0. Mm, this one is 0.
Yes, that will be 0.
This one not. And this should be 0. Then I'll get terms of the sequence. This is 0. This one is 0. Mhm. Okay. So this would be less than equal to b. Now this is yn minus yn minus y naught. And this will be y n minus 1 b square y naught plus y n plus 1 minus y naught. So instead of n plus 1, yeah, we should have taken n plus 2. So n plus 2, n plus 2. This is n plus 2, n plus 1, n plus 1. So this will be y. Now this will be less than b square
That was also
epsilon
fine.
by 2. There then we'll have to use n plus 1, but I have taken the definition in this definition for n greater than equal to n. So just, yeah, that's fine, but to be accurate,
Yes, yes.
okay, plus epsilon by 2. Now I'm saying that this is less than b square epsilon by 2 b square plus epsilon by 2, because again 2b square is less than 2 because b is less than 1. So b square will be again less than 1. So 1 upon 2 b square is greater than 1 by 2. So 1 by 2 is basically lesser than 1 by 2 b square. So this will get cancelled out. So we'll get epsilon. Therefore, yeah, we got mod fy naught minus y naught. This is strictly less than epsilon. Taking epsilon tending to 0, we get mod fy naught minus y naught. This is equal to 0. That is fy naught is equal to y. Hence, we got fixed point. And for uniqueness, again, we can suppose some other z naught in B such that fz naught is equal to z naught. In that case, we'll get f z naught minus f y naught. This is equal to y naught minus z naught. But what we already had, so yeah, this will imply that norm y naught minus z naught. This is equal to f z naught minus f y naught. And by the given condition on the function f, this is less than equal to b times norm z naught minus y naught. So this can happen only if b equals to 1. But we know that b is strictly less than 1. But since 0 strictly less than b less than 1, we get contradiction. Hence, we'll have a unique fixed point. So I hope you got, yeah, the proof was same. All we need to do is be careful about this why not. This why not should be an element, a point in B. So yeah, I wanted you to give some idea that why we are doing all this fixed point theory. Basically, while solving partial differential equations, we eventually convert those equations. We eventually convert our problem to solve partial differential equation into the form where we need to find critical points of some functionals like this, some integral functions. So if we can find derivative of some such functions, that's why I wanted you to see problems something like this. So if we can find derivative of such functions, that if we find critical points of these functions, we lead to solution of partial differential equations. So yeah, that's how this differential calculus is eventually helpful for further studies, further if you want to study partial differential equations. So I hope this was fine. This question number 4. I'll share this tutorial, whatever we have done on that Excel file. So you can go through this proof again and try the things that I have left in between. Yeah, I guess that's it. We'll meet on Sunday. Okay, let me stop recording first.